Stop! We're going to talk about brakes. How 3D printing and advanced materials make brake rotors better. This episode was originally broadcast live within the IMTS Spark platform. We're sharing it here as a regular episode. Brake rotors on the Cool Parts Show.
The Cool Parts Show is brought to you by Carpenter Additive. The company's Athens, Alabama Emerging Technology Center is an end-to-end additive manufacturing production facility with everything from materials development through post-processing under one roof, ready to help you with your next metal 3D printing job. Check them out at carpenteradditive.com. Now, back to the show.
Welcome to the Cool Parts Show Live.
This is our second episode through IMTS Spark. It's going to be similar to our regular show through YouTube or on our website, with the exception that our experts are here. They're going to be joining us in a few minutes.
If you're not familiar with the show, The Cool Parts Show, this is our show about ways that 3D printing is transforming manufacturing. Every episode, a cool 3D printed part, end-use part. Find all of our episodes at thecoolpartsshow.com.
Right, so every episode is about a cool 3D printed part. Today we have this flat, round, shiny thing. Pete, what is our part today?
This is a brake rotor. This is a brake rotor for car enthusiasts, made by car enthusiasts. This is a brake rotor for a Dodge Challenger Hellcat, competitive automobile. It's 3D printed, but it's also a new paradigm in brake rotors and how they should perform. A typical brake rotor for this car, about 32 pounds. This rotor, 12 pounds. Significant weight savings. And so that translates to greater acceleration, greater fuel economy. These lattices are dramatically more effective at heat transfer. So the heat transfer ability of this rotor is 5 times a typical rotor. Less surface area means less dust, less brake dust accumulation, 95% less. And because of the material, which we'll talk about, this won't rust.
Very cool. So lots to talk about, but let's start with the basics. Who created this brake rotor?
The company is Ceramic Disc Technologies, and they're a startup, but they're a spin-off out of a company that makes heat exchangers for aircraft engines. And a brake rotor does a lot, but it is in effect a heat exchanger, and Ceramic Disc Technologies is kind of discovering that a lot of what they know about the features that work well in a 3D printed aircraft heat exchanger also are really effective for brake rotors.
Okay, so a brake rotor is a heat exchanger. So I see that, like you pointed out, this kind of lattice structure that kind of fills the whole interior here. And yeah, like it looks like a heat exchanger. It has a lot of surface area that I imagine is there to help dissipate heat. But I want to ask you about something you just said, the name of the company, Ceramic Disc Technologies.
Right.
This looks like metal to me, but is there something else going on with the material here?
So there is a lot of surface area, like you say. So for the heat transfer, the geometry is very significant. But aluminum, which is sort of the initial thought for how to make a lightweight rotor, an aluminum alloy is not sufficient to provide the strength necessary for these delicate features, this delicate lattice under the load that this part needs to see. So a different material needed. This brake rotor actually is a metal matrix composite. At the microscopic level, you would see that this is it's not purely an alloy. It is a mixture of aluminum alloy and ceramic. The material provider, Elementum 3D, they're the developers of this metal matrix composite powder that it's possible to apply through laser powder bed fusion.
Wow, so that's interesting because the ceramic is bringing these benefits to kind of the end application. But from what I understand, like it would be really difficult to try and use laser powder bed fusion with like a straight ceramic. And so because this is that metal matrix composite, you can print with ceramic, but you can treat it more like it's an aluminum powder. You get kind of the printability of the metal along with the benefits of the ceramic.
Right, and so Elementum 3D, and we'll hear from them, but what they've developed, what they've discovered is Laser powder bed fusion is actually really good for applying a metal matrix composite. The melt pool is so small that it allows the aluminum to fuse around the ceramic particulate without these constituent materials separating or settling out in any way. And the result is, on a microscopic level, this very consistent structure of the material all throughout, resulting in this combination that really kind of gives you the best of both worlds: the lightness, the lightweight of aluminum, and the strength and temperature properties of ceramic.
All right, so we've got the material, we've got the process, powder bed fusion. What about the printer? What machine is used to make this?
EOS 400 laser powder bed fusion machine, so big machine for this process. Let me give you a good view. So the diameter of this part is such that it fills just about the entire area of the build plate of a big metal, laser-based metal additive machine. So when this goes into production, which it will, this is going to be a very big part for this style of additive manufacturing.
Yeah, so like a physically big win for additive. But I'm looking at this, and like there are areas that are clearly 3D printed, like this lattice surface. But then this whole top is so shiny and smooth. Like there has to be more to it than just the printing process, right?
Right. So as with most metal 3D printed parts, the 3D printing by itself doesn't tell the whole story. Yeah, shiny surfaces. A brake rotor. So it needs fine finish. It needs really precise parallelism between the opposing surfaces. You'd feel it in the drive if it didn't have those things. So precision grinding is necessary as a post-processing step to complete this part.
Okay, so I guess I want to get back to something you said at the beginning. So 12-pound brake rotor versus 32 pounds. That weight savings is coming somewhat from this geometry that you can create with 3D printing. It's also coming from the material, and those two things together are reducing the weight.
Yeah, so aluminum ceramic mixture has been used in brake rotors before, but it's been applied through casting. The ability to apply it through 3D printing allows for not just this lightweight material, but the lightweight material with a lightweight geometry. And those two things together like allow this very light brake rotor. And the weight savings on a brake rotor in particular are important. This is a rotating component, so particularly significant for acceleration benefits from the weight savings. This is part of the unsprung weight of the car. And so when I talk about a paradigm change in brake rotors, so lightweight brake rotors previous to this, 4 to 5 pounds savings would be a big win. This is about 20 pounds less per rotor as a result of additive manufacturing.
Yeah, so transformative weight savings. Like, let's talk more about the paradigm shift here in brake rotors.
Yeah, so let's bring in our guests, our two experts. So joining us is Michael Kowicki. He's founder of Ceramic Disc Technologies, and he's also the lead inventor of this brake rotor. And from Elementum 3D, our materials engineer is Adam Polizzi.
So, Michael, I understand that like this product really kind of comes out of your passion for cars, and we've been talking a lot about the weight savings. Can you tell us just a little bit about the kind of driving that you do and why reducing weight is so important?
The kind of racing that I do is called standing mile. It's roughly akin to quarter-mile drag racing, but whereas a quarter-mile drag race is focused on the launch and elapsed time, standing mile is really about power and the trap speed or the top speed. So in that racing, weight reduction is important or even critical. There's two kinds of weight in a car. There's fixed weight and there's rotational weight. A brake rotor obviously rotates, and so in a brake rotor, reducing that weight, that rotational inertia or mass is highly beneficial. And it occurred to me that with some of the work that we were doing with other heat exchangers that I could really combine the two, and ended up with the design that you have in front of you.
Talk a little bit about that design, Adam, or I'm sorry, Michael. Talk a little bit about that design, how you sort of validated this geometry, how you iterated and tested it. What kind of tools and methods were you using there?
One of the things that a brake rotor design has to consider is its streetability. Traditional brake rotors deal with, or have to deal with, all the environments out there: mud, snow, dust, dirt, rocks, that sort of thing. What we felt like was that traditional design accommodated those factors with too much weighting. And so what we felt like is we could give up some of that and gain a vastly increased surface area. You see the design. We've gone through a lot of iterations. As we did that, we did finite FEA analysis as well as thermal analysis.
So Adam, I want to ask you about the material. So by the time CDT came to you looking for a metal for this particular project, this metal matrix composite was one that you had already developed.
So the A1000 Ram 10, which is what the CDT rotors, brake rotors built from, is commercially pure aluminum. So it's actually not an aluminum alloy, metal matrix composite. So that utilizes our patented reactive additive manufacturing, or RAM. RAM utilizes our in-house production process to blend micron scale reactive constituents into the aluminum powder feedstock. And then also using the micron scale additives preserves the good feedstock flowability during the laser powder bed fusion process. So with these additions in place, they react in situ during printing and form submicron ceramic product phases that give the material the added strength, stiffness, and all-around increased performance at elevated temperature that you don't get out of traditional aluminum alloys.
So Adam, it's metal 3D printing, but it's not exactly and literally a metal, and I don't want to lose sight of that. It's a composite, and I wonder if you could talk about just the challenges of that. What are the challenges of laser powder bed fusion with a composite material, like at the microscopic level? Say, what's going on?
So one thing about the metal matrix composite, and the RAM especially, is it's actually solved one of the large challenges in aluminum materials and additive. So with laser powder bed fusion, one of the big challenges in the past was grain morphology, or the geometry of the grains that make up the solidified material. So the mechanism for part growth and powder bed fusion is in the Z direction, or layer by layer. So this has a propensity to form columnar grains that will grow skinny and tall and literally look like New York City got smashed together. So a consequence of this morphology is material property anisotropy, which is basically saying that the material has different strengths, different properties pulling this way than pulling this way, which makes difficult design issues. So during solidification with the aluminum RAM materials like A1000 Ram 10, the RAM product phases serve as a heterogeneous nucleation site, or particles from which the grains can initiate growth. So rather than getting your big, tall columnar grains, you end up with grains that are the grain morphology called equiaxed, which are commonly simplified as polyhedral geometries, or even spherical simplified to that point.
Yeah, so we've talked about the material, we've talked about the design that makes this possible. I guess my last big question for Michael, as a competitive driver yourself, what kinds of performance improvements would you expect to see on a car that was equipped with these rotors?
So you've asked me the money question. It's actually very difficult to answer that question accurately. The best answer I can give you right now is a quarter-mile drag racer might see on the order of 1 or 2/10 reduction in their elapsed time. But that might be unfair. The thing that people will tune into better than that is if you tell them that you're going to reduce their Challenger Hellcat by 75 pounds of rotational weight, that's what they're going to hear more than anything. And for their particular car or even other cars, that's huge. And that's what they're really going to hear versus whether I say, you know, they're going to lose 1 or 2/10 off their elapsed time.
Fair enough. Okay. I think I got this.
All right.
So this is a brake rotor for the Dodge Challenger Hellcat. It was developed by Ceramic Disc Technologies, 3D printed out of a metal matrix composite in aluminum with ceramic in it. So you get the lightweight and the heat transfer properties of the aluminum along with the rigidity, the strength of the ceramic. It has this kind of lattice design in the inside to help with the heat transfer as well. This brake rotor is 3D printed using powder bed fusion on an EOS M400 3D printer. And compared to a traditional cast iron brake rotor for this vehicle, which weighs about 32 pounds, this one weighs only about 12 pounds, which translates into that lighter vehicle, better fuel efficiency, hopefully faster speed on the track.
We've got time for some audience questions. We've got some questions from our audience. Michael, you said printing time for the rotor is 9 to 10 hours. When this goes to market, what kind of production volume do you anticipate?
The initial answer is that we'll be able to do about 300 cars per year. But that's easily increased by simply adding additional machine capacity. For example, you know, if we pick up one EOS 400-4, which is where we're currently at, you know, we'll get about 300 cars done per year. We can easily scale up. You know, 10 machines is going to do 3,000 cars a year. We go to 20, we're at 6,000 cars a year.
Next audience question for Adam. What goes into using DMLS, laser powder bed fusion, for ceramic aluminum? What's the process like? What kinds of laser parameters or other settings are important for working with this material? I guess, Adam, for someone who's used to 3D printing with say, an aluminum alloy, how is the process different? The actual settings and parameters of the 3D printing process?
So the settings are similar. They are different because it really depends on how much of our RAM is in the blended feedstock. As since it is an exothermic reaction, it gives off heat. It actually helps just a little bit with the heating process from the laser. So since we can use that heat and reduce the energy of the laser, we can travel faster and actually build at a higher rate in many cases.
Let's do one more question. And this one asks about a different brake rotor material. Michael, can you talk about the advantage of this material, this rotor design, versus a carbon ceramic rotor?
Right. So there's really two advantages to this versus carbon fiber. The first one is the big one, which is we believe we're going to be about half the price of a carbon fiber rotor. The other one is that while in some regards carbon fiber rotors are very durable, they have very high heat tolerance. They're also very fragile and are subject to chunking or cracking from impact. If you get a rock jammed up between the OD of the rotor and the caliper, for example, you can tend to damage a carbon fiber rotor. If they get impacted in the wrong way with debris, you can tend to crack a carbon fiber rotor. And so this rotor is, in that regard, is much more durable than a carbon fiber rotor, and again, probably about half the price.
All right, I think we'll end it there. That's all the time we have. Michael and Adam, thank you so much for joining us.
Thank you to our sponsor, Carpenter Additive. Listen to additive manufacturing podcasts, attend webinars, and learn more at carpenteradditive.com.